Here I'll be implementing an LRU cache with two methods. Get gets the key's value, or else if the key is not already in the cache, returns -1. Set, insert the key's value if it's not present. The least recently used cache is designed to store a certain amount of elements or items in memory and evict the least recently used element from that memory storage. I will use a doubly linked list and a dictionary to achieve this functionality. I'll start by writing out my own node class. It's going to store the key and the value. And it's a doubly linked list, so you can access the previous or the next element of each node. As I mentioned, the node will be constructed of a key and a value. And that ends the node class. On to the LRU cache class. I'll need two integers, count and max count, to store how many elements are in the list and the maximum capacity of the list. And I'll need to define two nodes, head and tail. I will initialize a new dictionary. That stores an integer and a node. Name it dict. One of the problem definition statements is the capacity of the cache needs to be set in the constructor for the class. So this is what I'll do here. The user can pass in their desired capacity for the cache. Initially, there will be no elements in the list. And here I've created a new instance of this object. So we're going to want to be able to do a few things that we will reuse, so I'll write those as private methods. I will, yes. we're going to want to place elements at the head of the doubly linked list when they are first set, because at that point in time they'll be the most recently used item. And remember, we are going to be kicking out the least recently used items. So there are two cases here. If the head is null, we need to assign that input node to be the head and the tail. I'll close this off. It will look a little bit messy, but I want to fit place at head. I want to fit everything right here. And so here we assigned this input node as the head and the tail, and here we are making this input node to be the new head. So we're taking the like if we have a linked list with 3 elements in it, we're adding the 4th element at the front, so we're gonna swap around those pointers. And close off this else, and close off the private place at head method. We also need to be able to remove a node from its current position. There are 2 cases in this implementation of my doubly linked list. There are if the node is the tail and if the node is not the tail. So let's handle if the node is not the tail first. And yeah, I'll leave it at that. if the node is the tail and we're removing it from its position. Close off that private method. Okay, and now let's write out our getter and our setter. So if the dictionary contains the key and it is not the head, we'll call our private method. So if the dictionary contains the key and we're not talking about the head, we will remove that node. So here x is the key and dict of x is the value. The value of the dictionary is going to store the position of the node. So we're passing the node's position into our private method remove from position. Let's keep our parentheses consistent here. So we remove the key from its position and we place it at the head. What our doubly linked list is doing is maintaining the order in which these elements have been accessed and set. And then we're going to return this node's value. Because we've stored a value parameter in the node. Not to get confused with the dictionary's value. And if the dictionary contains this key and head.key, because like I just mentioned, every node is storing a key and a value here. And the dictionary is storing the key as its key and the value as the location of the node. So if this node is the head node, we are simply going to return the value stored in that head. Else would mean that this key is not available at the head or anywhere else. We are going to return -1 as requested by the problem statement. And close off the get method. On to setting. This is taking so many pages. So we need to check if the dictionary contains the key. If it does, we will set, hence the method name, the value of that node as y. So this is handling the case where, let's say the key already exists in the dictionary, but somebody wants to set and update that value. That's what this is handling. So if you're setting something and it's already contained within the dictionary, then we're going to remove it from position and place it at the head because it's the most recently used element at this point. Else, which means this element that we are setting did not already exist in the dictionary, will increment count, which is storing a count of the number of elements in our doubly linked list. Because we cannot exceed max count, so if count exceeds max count, which is our capacity, then we have to remove the last element. From the last element in the linked list, we have to remove it from the dictionary and from the linked list. So we will remove tail.key, which is tail's key that we stored. Remember, in each node we're storing key and value, and the keys in the doubly linked list match up to the keys in the dictionary, so removing the dictionary element with key tail.key. Now we have to chop this off of the tail. And decrement count, because we have removed an element from our list and dictionary. Now we need to So this handles the case if we're at capacity, but either way, we need to put a new node at the head. So we'll create new node of type node, create a new instance, pass in x as the node's key and y as the node's value, place at head of new node. And very nifty, now that new node is the head, we can simply add to the dictionary x as the key and head as a value, which is the location of the head. So we will close off our else, close off our set, and we also, at long last, get to close off our LRU cache method. So now the most time efficient way to discuss what's happening in this algorithm is to represent it visually instead of going line by line. There are over 100 lines of code here, and yeah, so let's just get started with that representation. So we have some driver code. Let's create a new cache, if I can spell today, of size 3. That will pass this in as max count. Okay, so cache dot set, we will set 1 as the key and 10 as the value. Cache dot set, and this belongs in the static void main. This is our driver code that we're using here to interact with our LRU cache class. We'll set 2 and 20. We will set 3 and 30. We will get two, and we will set 4 as our value, or 4 as our key, and 40 as our value. Okay, so this is what we'll be doing. Whoop, whoop. We have I think we have enough room. Yeah, we have enough room if we do this over here. So let me draw out our dictionary. Lower that. Our dictionary and our doubly linked list. And let's get started with what's going on here. So our max count has been set to 3, which means the maximum number of elements that can be in our doubly linked list is 3. So what's happening here is we're setting this key value pair. So 1 comes in as the key, and a new node is created, put at the head of the doubly linked list with, how do I draw a doubly linked list? With its key and its value. Its key is stored as 1, value is stored as 10, and our value in our dictionary is the location of this node. So I'll represent that by showing node of the key. Okay, so now we're going to set 2 and 20. So 2 comes in here. Now, okay, I'll have to erase this, but a new node is created with key of 2, value 20. 2 is placed at the head, so I'll just put 2 and 20. 2 is placed at the head, and 1 is no longer the head. And the location of this node is stored here. Now 3 comes in. 3, again, well, let's just do this. Oh, but you can't see that, okay. So 3 and 30, and the location of the node stored here. We're gonna get 2, which swaps 3 and 30 was at the head, but now 2, 20 is at the head, and 3 and 30 is here. We're going to set 4 and 40. Okay, so we're at capacity. This this means that we're going to, oh, it's on this page, great. We're going to remove the tail and decrement count, and then it's also getting removed from the dictionary. And for, okay, you can see that 4 and 40 is now at the head. So if we were gonna try to get, let's say get of 1, if we were gonna try get of 1 after this 4 of 40, we would not be able to get it. Oh, 4 was inputted here. Because it's not maintained. The max count is 3, so the maximum number of elements that can be stored is 3 in this cache. Okay, and we can also assess the time complexity and the space complexity for this algorithm. It's awesome because we do sacrifice a little bit on the space complexity, that is O of n, but the time complexity, because I created my own node class where I could store both key and value, we are able to perform both our get and our set method in constant time. Not linear, in constant time. Awesome.